Okay, so today we do some real arithmetic, start doing some real arithmetic. Yesterday was all philosophy. So, what we are interested in is obviously equation of manipulator in joint space, because we want to know what are the joint talks. So, there are two basic formulations. There is a Lagrange formulation. So, we will use that equation of partials and derivatives using that silly function t minus v, and then there is Newton-Euler formulation, and this one obviously uses the fact that if a free particle moving with constant velocity, then all free particles move with constant velocity, and the fact that force is an entity which is independent of the mass it is being applied to and things like that. So, you can make your pick. So, there are this Lagrange formulation is very systematic. I mean, there is no variation, you just have to crunch. You crunch and you crunch and you crunch and you get a formulation. Okay. In Newton-Euler, particularly for open kinematic chains, that is of the kind in which you have manipulators. Now, the Stewart platform is not open kinematic chain, it is a closed kinematic chain, because you can run a loop from say link 0, which is the base, you go up to the end effector and then you come down. So, you close the loop. So, it has got several closed chains like that. For that it is not very effective, but for open kinematic chain, this what is called the Newton-Euler recursive formulation is computationally efficient. So, that is very nice. And the second thing is, after we do this, we get into what is called dynamic parameter identification. Now, when I do the equations today, you will see lots of terms floating around. It is very easy to define mathematically. Okay. So, for example, moment of inertia, right. You know what moment of inertia is, and you know what mass is. Have you ever measured mass? Yes, no. We measured weight, right, and then you can divide by g and you know mass, and then theoretically with the spring balance you could measure mass also. Can you?
You can measure mass by comparison to known masses.
By known masses, or you could take a known mass and pull it with a spring and see how much it accelerates. So, you could do that also. So, you could measure it. How do you measure moment of inertia?
Take the body about particular axis, apply torque and calculate angular acceleration.
Calculate. Do you know a method to measure it? At least you can measure weight, and so you can figure out mass, you have a balance. Never asked yourself. It is not part of our robotics syllabus, by the way.
Calculate it from the mass and the geometry of the.
How do you know you are doing it right, You could be using something very silly to calculate. You need to measure it, right? No? See? It should be testable, right, against the empirical world. So, your calculation is as good as somebody else's calculations. Anyway, so have you heard about the Trifler pendulum? No? Yeah. You should look it up. So, it is a very simple device. You take a disc and you suspend it from 3 springs, and then you put the object in the middle, and then you set this into oscillation. Okay. So, as this oscillates, there will be a, so the string twists, another string twists, the cable basically bends in space. So, it is kind of like a pendulum. So, there is a, so every time it twists, it goes up in height and then it unwinds and comes down, and then it again goes to the other side. It is like a pendulum. So, you can show that the time period of oscillation is dependent on obviously the length of the strings and the radii on which they are suspended and the moment of inertia of the disc. So, this is the standard way of measuring moment of inertia. So, you can measure it, then you need to turn it around, put it about the other axis, then you put it about the other axis, so you can measure. Okay. And so, in general this is difficult, okay, identifying the dynamic parameters if you have to measure it. And so, there is this method by which you can identify these various dynamic parameters, and some of it you may know, you may not have the CAD model of that, you may not know the densities, you may not know every part. Somebody will give you a CAD model but will not tell you where the screws are. Okay, so, you can essentially go through a process of dynamic parameter identification, which is important to implement the control. So, that is one of the problems. Now, there is direct dynamics. Well, there are two problems essentially, that given the joint torques, find what the motion will be. Other is given a set of motion, find out what will be the necessary joint torques. Now, you would have done both of these problems in your mechanisms course, right, for the 4 bar. Both of these. For the 4 bar problem, what is the joint torque to get a certain motion, and if given a joint torque, what is the certain motion. One is more difficult, one is easier. And then we are looking at dynamic scaling. Oh, and so this part is interesting because when I finally want a desired motion, I need to give joint commands to the torque. This is interesting if you are building a simulation of the system, okay, that given motor torques you want to see how thing whips around. So, there are two different ends of it. Then there is this concept of dynamic scaling. So, what you do here is, so far when we did trajectory planning, we just did kinematic planning, right, and we saw when we did kinematic planning that depending on your selection of your decision that you make, you have more acceleration or less accelerations. Okay. Now, in kinematics we do not worry about it, somebody will provide the acceleration, and we generally understand large accelerations are not so desirable. If you can do it with a smaller acceleration, that is the preferred method. So, the idea is that you, now that you know dynamics, which I did mention that moment of inertia is not invariant, so there is a problem. So, once we learn dynamics, we can come back and revisit trajectory planning very briefly, just to understand what could be the issues. And finally, we need a dynamic model manipulated in operational space, because I started with a joint space. Nice to have it in operational space, and then look at something called the dynamic manipulability ellipsoid, which you can calculate, which tells you that if you are there at a particular location, which way, movement in which direction is easy, is preferred, in which direction if you can you get higher accelerations, higher this thing. So, that can in some sense help you plan your trajectories and applications. Okay. So, for example, I know very well that if I want to lift a large weight, I will want my hand roughly at 90 degrees. Okay. It is not a good idea to lift a large weight like this. So, there is a change, and that will obviously affect the decision when I am planning. So, where do you get the links in? So, it is a large basket of problems, enough to keep somebody busy for a year just doing this in great detail, trying to understand what happens. So, I intend to dedicate only about 2 weeks to it. Okay, so we'll have a good time over the next 2 weeks. Okay. So we start by looking at the Lagrange approach, okay, because that's quite systematic. This equation we already visited, so I will not worry about it, and especially this extended form where there are n generalized parameters. In this case it will be the link rotations. So write it in this form, and so this is slightly extended. Instead of writing q I n is I is equal to n, you just stack it together and you define a vector q, which is the vector of joint angles. So this is just alternate form, it just allows you to make it more compact, that is all. Instead of writing I is equal to n all over the place, simply define the vector. Especially electrical engineers love doing this, and because the examples we will look at are small, we will obviously not look at the 6 by 6 example in the class, though you could extend this method in general. So we assume that the links are rigid. Okay. If they are not rigid, we will have additional problems. What are the additional problems? We will have the elastic energy also, which is which will add to the potential energy, number one. Number two is the kinetic energy we will write very simply in terms of the motion of a particular point and the angular velocity of that link and the moment of inertia of the link. Now if it is a flexible body, then that goes away, then the kinetic energy becomes a more complicated term because it is reconfiguring itself. So you got to find out, and in doing this the moment of inertia will change as a function of time, even in the local frame. So currently we account for the fact that moment of inertia is changing in the global frame, but at least in a local frame it is constant. So after that we just need a rotation matrix, which you are experts at already, right, to take care of. So we do not have so much of a problem. So in the first cut we look at rigid links, but it is also interesting to know what were the deviations which will come around when you are doing flexible. Let me come back here, I forgot to emphasize on this. So Zi is the generalized force. Now there are two kinds of forces, conservative and non-conservative. This you must remember from your mechanics. What are conservative forces? Work done in a cyclic path is 0. If it is there, then those forces can be expressed as the gradient of a potential function. Okay. So then it goes into the potential energy term. You do not have to worry about them. So that goes into the potential energy term. What does not go into the potential energy term is classified as the generalized force, and so you would have friction, actuator torques, end effector forces. These are all added into the generalized force at the appropriate axis. So that is the added thing which I simply forgot to question, and well, you are supposed to read this and interrupt me. What is this? Or you understood it? Right? You do not read, what is there? I do not blame you. Why don't I blame you? See, because there has been statistics done on human beings, and it says that somewhere close to median is 17 seconds that you can hear and see at the same time. After that you can either hear or you see, you do not do both. So when we use a blackboard, so we are writing is a laborious process. So when I am writing, you can see what I am writing, and then I turn around and talk, right. So that is very nice, because I can't turn around with my face to the, I mean it is not nice to talk with my face to the blackboard and my back to you. So now when you go into this mode, things are very fast, right, because I am talking and then I keep scrolling my thing, so I need you to look at this and listen to me. So the limit is 17 seconds. It's got to do with robotics. It's got to do with cognition. So, if you're making advertisement, right, please keep it below 17 seconds, otherwise you lose context. Okay. Nice. So, please take time and stop me, otherwise this is very easy. Okay, I will just run through it in 30 minutes. So, what we do is, if there are n rigid links, so I am going to take the kinetic energies of the link structure itself, and then there is a motor. Now, I need to treat the motor separately, because the motor is a funny structure. So, one part of the motor will be attached to some link or the other, and the rotor part will either be directly attached to another link, or it will be attached to another link through a transmission, through a reduction drive, or a typically you reduce because you want to increase the torque, and motors are fast enough, especially electrical motors. Speed is not a problem, torque is a problem. So, there is a step down drive, 100:1, 50:1 is the typical ratio that you are interested in. Rare cases you go in for with a epicyclic drive, which is much higher ratio. So, it needs to be handled separately. It can be ignored depending on what you are doing, but usually, so for example, you went and had a look at the KUKA or these robots, you must have gotten the feeling that the structure is quite light, it is the weight of the motors which is creating a huge mess. So, for a 5 kg payload, I mean the motors, total motors in that must be weighing close to 70-80 kilograms. So, it is important, and even the rotors are quite heavy. It is not that the whole weight is in the shell. So, that needs to be taken care of, and it is a little different, so it needs to be handled. And so, you know that the kinetic energy is essentially defined for a particle, right, and this you already know from mechanics that you want to add it up. So, there is this density rho with which you will multiply dV, and you integrate this, and so you can finally get it down into this form. I am missing a bracket here which I will insert later. Okay, so, but this is not very interesting, writing down the kinetic energy and the moment of in terms of velocities and this thing of points. So, we need to get it in terms of time derivatives. What am I doing? Sorry, let me recant this. I am now first looking at the potential energy, which is much easier. There is a gravity term and there is a position term, okay, and this integrated over rho over the volume. Now, rho dV will essentially give you the mass, okay. So, the mass pops out for both of them. So, there is a mass term which is here, and then gravity, and then just position of the center of the link. So, these are the terms which are there, and it is very simple. You can find the position center of the link because you know DH parameters, you know the joint angles. So, you can find out position of the center of mass, and you also know velocity of the center of mass, right, without great difficulty. Now, the kinetic energy is slightly more complicated. So, there are again two terms due to the link and the motor. So, if you take the link I, again you need to integrate over the whole link, but you know how to do this. So, you get two terms when you do this. One is the mass of the link into velocities of the center of mass of the link, okay, and the other term is due to the moment of inertia. Well, actually there are three terms, right. There is due to rotation, due to translation, and so there is something called the mutual coupling, which in this term the center of mass is defined as a point where the mutual coupling becomes equal to 0. so that you can go back into your Shames or your Merriam and you can look it up. So, but since this is primarily a mechanical engineering class, we can say quite confidently there will be two terms, mass into velocities of the center of mass and angular velocities into a rotation matrix which has to be defined with respect to the base frame. Now, the rotation matrix with respect to the base frame is not fixed. In a local frame, the inertia matrix is known, so this has to be transformed into the base frame. So, you need to multiply with two terms, the rotation matrix comes pre and post, right. That is the standard transform, because you have to go to the link, do that and come back, and this rotation matrix transposes the inverse operation. Okay. And this rotation matrix, obviously the inertia tensor you can obviously find out, you know enough methods to do that. Otherwise, if you have a CAD model of the link, it will tell you what it is. Number one, it will give you a reasonably good estimate. However, later on you can go back and you can re-identify and you can correct the model. Now, in this form, in this omega and PLIT, we do not have these terms in the joint coordinate system. I need that in the generalized coordinate system. So, what we are then looking at overall in terms of coordinates here is that there is the center of mass which is here, and there could be a particle at a position Ri in the local frame which will be at this point Pi star, and the velocity of this point could be in some other direction P dot L1, and then this has angular velocity omega I. So, these are general terms which is there. So, now so we already know how to find velocities of anything we want under the sun as far as the links are concerned, because we know about Jacobians. And usually what we have been doing is that we have always talked about the velocities of the end effector when we find the Jacobians, but that is not a sacrosanct point. You already know that you can find that of any point on the link or any other link. The only thing is that now if I am talking about the ith link, finding the velocities in the ith link, I will have to involve q1 dot to qi dot and a corresponding Jacobian. Okay. And so, this in general will be a composite which I am calling JPLI. If I am interested in the angular velocity, I will have again a different set of terms, and when I cascade these together, I am calling this J0 Li, and this multiplied by the matrices. Now, we know that. The only statement which I am making here is that if you are interested in things which are on the third link, you do not need the Jacobians of the screws of the fourth, fifth and sixth link and the corresponding parameters. So, when you go to the fourth one, you need the first four, then you go to the fifth one, you need the first five, you do not need the last ones when you cascade them. Now, each of these terms consists of, so if you take JPI Li, so there will be two terms. So, if it is a prismatic joint, then this is just Zj minus 1, and if it is a revolute joint, then it is Z of j minus 1 into the vector from the origin to that location of the joint. So, you will have these additional terms for a revolute joint, and similarly for the omegas, it is if it is a prismatic joint, contribution is 0, if it is a revolute joint, contribution is Zj minus 1, this is a vector. So, just write down the 3 vector and then you are in business. Okay. So, you can form these and then you can write the TLI to be, essentially you will end up with a large expression like this, and obviously the idea is that you are using something like MATLAB to do it. Okay. Well, you can do it, you can do planar problems which are much simpler by hand, and many of the terms will drop out, right. Okay. So, we'll end up with a large expression like this by cascading it together. So, half mv squared terms, half I omega squared terms, and then you can calculate it through the Jacobian root. Now, everything here is in terms of the q dots, and everything else is geometry. So, you need to be able to do forward and inverse kinematics to come so far, but everything else is geometry, and this is the mass property, this is the moment of inertia property, which is fine. Now, when we are talking about the motor, so there are two parts, right, this stator part and the rotor part. Now, this is a very schematic diagram. The rotor is not necessarily a thin spindle which is sticking out. The rotor internally, it has windings on it. Okay, so there are two kinds of motors which are there, moving magnet and moving coil. Okay. So, the originally motors used to be moving coil, but now they have often become moving magnet motors, especially the high torque motors are often moving magnet. So, this spindle internally becomes a much larger structure with a diameter, and this could be, I mean, this is a belt is shown schematically, but there will be a reduction factor between here and here, and this need not be located at this joint either. It can be located at a location which is other than this joint axis physically, and it may not be halfway down to the other joint, but could be in proximity, but could be off center. Okay, and there is a reduction drive and coming off the other side. So, so what we will do is we will club the properties of the stator with the link, no big deal, we can do that. And this rotor needs to be handled separately, especially if there is a gear reduction. Now, the basic thing is the omega of the rotor is not the same as omega of the joint. Okay. So, we can write the net kinetic energy of the rotor in this form. So, the terms here are mass of the rotor, linear velocity of the center of mass of the rotor, inertia tensor of the rotor relative to the center of mass, and the angular velocity of the rotor. So, these are terms involved, you can pretty much write these, and so you can relate the angular velocity of the rotor to the angular velocity of the link on which it is located plus the angular rate of the next joint multiplied by the transmission ratio along the axis of the motor. So, it is not that difficult. So, it is still difficult to write down ab initio in an exam, but if you are given the A4 size sheet of paper, it is not so bad, okay. Or if you have a book with you, then it is not bad at all. And then you can expand this similarly in terms of Jacobians, and you will get an expression which is large and big and looks very similar to the term of for the link. So, this is one of them. The only thing is the relevant Jacobians are different. Okay. So, in that case, through the Jacobian we are trying to find the Jacobian which is relevant to find the velocity of the center of mass. In this case, we are trying to find the Jacobian which is relevant to the center of mass of the rotor. And the rotation matrices could be a little different, which is the rotation matrix on which the link on which the thing is the rotor is situated. Well, there are some assumptions here and there in the middle that that the rotor is symmetric about an axis, otherwise you will be in trouble because you will need a matrix dependent term which is dependent on that, so on and so forth. So, that is okay. If you can start with t minus v, we can take these little things into place. So, finally, after you summed it across all the motors and all the links, you get a very simple equation of this form, half q dot t into bq q dot. Okay. So, this is really simple. What is not simple is bq, which is essentially I have just added the two terms together. Okay. And so, B is then called the inertia matrix of the robot as a system, of the whole manipulator as a system. It is more complicated than a normal inertia matrix, but it is still symmetric like inertia matrix. It is positive definite. Okay. So, all the eigenvalues are positive. That has some very nice properties. Okay. You can show that Newton-Euler equations are invalid if the net system inertia matrix, or you cannot use many of the operations if the net system inertia matrix is not symmetric, if it is not positive definite and things like that, a lot of problems. So, if you have done a course in classical mechanics, you all have done a course in classical mechanics, right. So, you should know these things, and the last part is the biggest catch, which is the fact that it is configuration dependent in general. So, this obviously changes as q changes, because as q changes the j's will change, the r's will change. So, it is not constant, and so that is what makes life very easy. Okay. So, the rest is very simple, right. You just have to go back, write the Lagrangian, right. You know T and you know U, and you write this equation, and you have the dynamics equation of the manipulator. Okay. So, at the end of the day, I will go back, I will upload the notes, and I will upload a sample problem. Now, you should do that, but let us make you submit it. Okay, I will upload it today. So, based on this I will upload a sample problem. You are still smiling. So, you please bring it in on Friday, so that you are initiated into this process and you realize it is not as bad as it seems to be out here when it is written in terms of script L and things like that. This really turns people off, script L, and have you seen that other R which you write like this with 2 R's and things like that. So, that really turns some people off, mathematicians love it, right, and it really turns some people, the moment they see it, they say I do not want to study this. So, two ways of it. So, it is not really that bad, this is actually quite simple and very, very direct. You just have to be systematic, and you should have done it before. So, these are the two things which are relevant here. Okay. So, we will stop here.